think it's working. All right, I'm going to try and do a high resolution recording this time. Lately the recordings have been poor, and so I'm trying something a little bit different, just to see if we can't get things to work a little bit better. So we've got a homework due on Monday, and that would be homework number 7. So I think that would be, see if I can get this on the page. Update rate is not so good. Homework 7 is due Monday. And what I would do, since you guys have had a chance to look at the homework and make a decision about what it is you find difficult, is I would open the floor to questions about the homework. Does anybody have any specific questions that they might like to see me cover in the homework? Homework set. Sure. Let's see if I can bring that up. Number 1. Which of the following is a correct sign and magnitude representation? So let's do this. Suppose we have the number 5, base 10, and we want to represent it as a positive number. So in some sense, sign and magnitude is nothing more than the number 5 in binary with a placeholder designed to hold the sign indicator. If it's negative, the sign indicator is a 1. If it's positive, the sign indicator is a 0. And so positive sign and magnitude, right? This is the magnitude part. This is the sign part. And as it happens, 0, 1, 0, 1 is a correct sign and magnitude representation. So then comes positive 7, base 10. What would we do for sign and magnitude? Well, if it was 1, 1, 1 and it was positive, this would be correct. But we see B is not correct. It doesn't look right at all. And then, so this is A, so that looks all right. B, no, that doesn't look right. C, it says here we want negative 4. Negative 4 base 10. And so that must be equal to 1, 0, 0. It's negative, so there must be a 1 for the sign part. And that looks correct. 1, 1, 0, 0. That is correct. And so then there's an option D, and option D says A and C are correct. And so that's the one that you want to pick. What do you think of that? That's number 1. Does that sort of answer your question? Sure thing. Sure thing. What other questions do you have for me? You betcha. Let's see. Which of the following is correct? The 1's complement. All right, so this is 2. The 1's complement of 0, 1, 1, 1 is, well, first of all, 1's complement would just be invert. That's the 1's complement. So then it would be 1, 0, 0, 0. So his answer of 1, 0, 0, 1 is not correct. Then he says, what about the 2's complement of 0, 1, 0, 1? So 2's complement, you form the 1's complement, and then you add 1. So that would give me 1, 0, 1, 0 plus 1, which gives me 1, 0, 1, 1, which is also not correct. So it says which of the following are correct, and we're not getting this answer here. So the third thing says the 1's complement of 0, 1, 1, 0 is 1, 0, 0, 1. And that is correct. So that's good. Then the other thing it says is the 2's complement of 0, 0, 1, 1. That would be 1's complement plus 1. So that would be 1, 1, 0, 0 plus 1, which is 1, 1, 0, 1. 1, 1, 0, 1 is not what they're giving us for the fourth option. So the only option that is correct is the third option, and that is D. So that's number 2. Any questions about number 2? Moving on to number 3. Okay, number 3, kind of changing the subject here. Which of the following binary multiplications is correct? All right, so what we got here is 1, 1, 0, 1 times 1, 0, 1, 1. And so I have 1, 1, 0, 1, because it's that times all of this. Then I have 1, 0, 1, 1, because it's that times all of this shifted over. Then I have 0, 0, 0, 0, because it's 0 times all of this. And then I have 1, 0, 1, 1. And now I do a simple addition. 1, 1, 1. 1 plus 1 is 1, 0, plus 1 is 1, carry the 1. 1 plus 1, that's 0, carry the 1, 0, carry the 1, 0, carry the 1. And so now I have 1 with 3 zeros and 4 ones, and that is base 2, and that is a correct answer. Now, what is this value over here? This is base 2. What is that equal to in base 10? So I got 8 plus 4 is 12, plus 1 is 13. And then this one is going to be 8 plus 2, which is 10, plus 1, that's 11. And so now I break out my calculator and multiply 13 times 11, and I get a number 143. Now let's see what this number is. 0, 1, 2, 3, 4, 5, 6, 7. So that's 2 to the 7, which is 127. Plus 15, which is 2, carry the 1, 4, sorry, did I make a mistake? Huh, looks like it's 142. Tell me I did something wrong. Let's see. 1, 1, 1, 1, that's 15 for sure. This should be, maybe that's 2 to the 7 is 128. That's where I went wrong. And so that is 143. Base 10. So that's that. So multiplication works. Thank goodness. And so that's the answer to question 3. It's A. Any questions about that? Sorry for my blemish. I got the 127 when I should have wrote 128 because it's an integral power of 2. So 2 to the 7's got to be an even number. All right. What else? Other questions for me? Let's see what we got here. Now, 10. 10, I believe, is in the book. Let me just sort of check that one. So I have a feeling this looks familiar. Yes, indeed. Yes, indeed. Right. Let me see if I can get this onto the camera. Oops. Here we go. So this is full adder, full adder, full adder, full adder. And these are the carry-ins. And here is an exclusive OR, which is being used for the overflow right in through here. And so when you are reading the book and following along with the text, it's helpful if you'll use the text and try and answer some of your questions, so it's clear, when what's in the box, and the answer is overflow. And let's see, these little bitties in here, these are 2-to-1 multiplexers, but they appear to be replaced by the exclusive OR, which is essentially adding 1 when there's someone asserting the subtraction facility. So what they're doing with the add subtract line, the complement, there's the complement part, and then increment by adding 1 to the carry in, and now all of a sudden this adder circuitry is doing 2's complement subtraction. So not add subtract means when it's 0, it's going to be adding. When it's a 1, it's going to be subtracting. So then putting a 1 in here adds 1 to the quantities and selects the inverted version of B. And as a result, it gives you the, 2's complement, right? So this is the complement and increment of the accumulator. And so we can reuse the full adder circuitry using the add subtract, the not add subtract input line. And you can make this as long as you like, but of course the more bits you add, the longer the delay. Now there are ways around this, and they're discussed later on in the use of the so-called carry propagate look-ahead generators, which allow us to short out some of the computations, but we haven't talked about that yet, and it's not in the homework, so I don't want to digress too far. Does that sort of answer your question about that one? That was the answer to question number 10. Comes right out of the book. And the other one, any questions about that? So the other one was 11. So let's go to 11. Well, it seems like the exclusive OR is the answer, so that would be, yeah, that's B, because you can see exclusive OR is being used for the overflow in the book. Sure. Let me put the book away. All right, now let's have a discussion about light-emitting diodes. So a diode consists of an anode and a cathode. These names date back to Michael Faraday, interestingly enough. And this is the negative side. And so what you're looking to do is form a mechanism of illumination. And we know that illumination, we can illuminate from heat. This thermal illumination is different than the kind of illumination we expect from an LED. When we illuminate from heat, we incandesce. And we use very high temperature elements for that, such as tungsten, which has the highest melting point of any metal we know. And we make a tungsten filament and put it in a vacuum, and it gets so hot that it becomes white hot, but it is in fact very hot, and it's an incandescent bulb. We have other bulbs where we have an ionic plasma in a tube. We call it a fluorescent tube, and the little electrons bounce off phosphors, and the phosphors emit photons, which are at a lower energy level than the electrons, and they can be at different, they call them color temperatures. Color temperatures refer to what temperature an incandescent block of graphite would have if you had a block of graphite and raised it to 5,000 degrees Kelvin and had a hole drilled in the center of it. The block would get to be the color of what they call daylight, 5,000 degrees Kelvin. And what that does is it gives you a calibrated source of spectral output, which you can then equate to those things like the fluorescent bulbs, which don't quite need to be heated to 5,000 degree Kelvin, thank goodness, in order for them to give you the type of light that a 5,000 degree Kelvin calibrated light source would give you. So these use fluorescence. And then comes the LEDs. And the LEDs are using a form of illumination known as electroluminescence. And the electroluminescence occurs when electrons combine at the region between the positive and the negative material. And that is created by taking silicon or some other semiconductor such as gallium arsenide and doping them with extra P material and extra N material, and that dopant allows them to have a deficiency of electrons or an excess of electrons, so that when electricity flows, when a current flows across the junction, a recombination occurs and photons are emitted from the junction. And so that's the basic principle behind these sorts of things. And so we have electrons going from one energy level into another, and as they drop from one energy level to another, they emit a photon. But in the process, there's a certain inefficiency that occurs. There's a voltage drop that occurs across the barrier. And that voltage drop, and this is described in some detail in the book on page 669, I'll just write that down, is a classic 0.7 of a volt. And that gives you an inherent inefficiency, right? Because if you have a 3 volt diode and it wants to drop 0.7 of a volt, that 0.7 of a volt gets converted into heat. So if you know that you're running an amp, right, then you know power equals current times voltage, and the voltage drop is going to be, I don't know, perhaps 0.7 of a volt, and here comes an amp, and now all of a sudden it looks like you're having to dissipate something on the order of 0.7 of a watt, which could heat up and eventually destroy your junction unless you can dissipate the heat appropriately. Did that sort of answer your question? Probably more than you wanted to know. Okay, good. So one of the things you might encounter is LEDs have a long side and a short side. And the long side is a long lead and the short side is a short lead. And this is going to be the part that goes to the positive side, and this is going to be the negative side. And that'll be your anode, and that'll be your cathode. Let's see, what else do we have? Any other questions? Sure. I think it's time for a fresh sheet of paper. Okay. 4. 7 base 10 minus 1 base 10 is 6 base 10. Let's see if we can do that using 2's complement. So we have 7, which is 0, 1, 1, 1, base 2. And now, how do I do minus 1? Well, let's see. 0, 0, 0, 1. Oh, sure. Sorry about that. Base 2. So I wanted to increment and complement the accumulator. So here comes 1, 1, 1, 0 plus 1, which is 1, 1, 1, 1. Base 2 equals minus 1. So let's get 1, 1, 1, 1, base 2, and then we'll add it together, and we'll get 1 plus 1 is 0, carry the 1, 1 carry the 1, 1 carry the 1, 0, carry the 1, which falls on the floor. And now I have an answer, which is 0, 1, 1, 0, base 2, and that happens to be equal to 6. And that is A. What do you think of that? Is that any questions about that? That's a very fine question. That is, well, there's the hardware answer, which is we don't accommodate the leading one, so when there's an overflow, we can light up the overflow light, but we don't use the overflow in the next column because we didn't accommodate for it with another adder. So the answer is because we don't have another full adder coming out. So that's a, if we had a full adder and we kept going, we could keep going with that extra 1. Yes, sir. That is correct. This is 0110, which happens to be letter A in the answer key. What was the other one? 5? Yes, sir. Oh, well, it said it wanted to subtract 1. So I wrote down 1 in base 2. And then to give it negative, I made a 2's complement by doing a 1's complement and then adding 1. So when I did the 1's complement of 0, 0, 0, 1, I got 1, 1, 1, 0. And when I added 1, I ended up with 1, 1, 1, 1. How's that grab you? Sure thing. Any other questions about this one before I proceed? Alrighty then. Yeah, because that's my next one. Just like to. Okay, this is a bigger one. Big question. 5. It says, what is the output for an 8 by 8 multiplier? That's a lot of bits, isn't it? If the input is 1, 1, 0, 1, 0, 0, 1, 0, and 2, 4, yeah, there's 8 bits there. 1, 0, 0, 1, 1, 1, 0, 0. And you want to multiply. Did I write that right? It looks all right to me. And that looks okay too. Okay, got to write down the correct question before I try and answer it. So this is 0. Because anything times 0 is 0. And then this is 0. And I'm just writing in all the zeros here to keep things lined up, and I'm using graph paper to. There's a lot of numbers around here. And then this is going to be 0, 1, 0, 0, 1, 0, 1, 1. Neatness counts. And then 0, 1, 0, 0, 1, 0, 1, 1. And then 0, 1, 0, 0, 1, 0, 1, 1. And then 0, 0, 0, 0, 0, 0, 0, 0. Running out of room. I should have wrote it over further. And then 0, 0, 0, 0. Uh-oh. Going off my edge here. And then, let's see. 0, 1, 0, 0, 1, 0, 1, and here we are off the edge. Just in time. Now we have to add all this stuff up. Unless I've made a mistake somewhere. That looks kind of funny. Let's see, that should be a 0. Anything else? Yeah, it's looking all right now. So that's 0, and that's 0, and that's 0. That's 1, that's 1, that's 1. That's 1. That's 1. That's 1, carry the 1. 1, carry the 1. 1, carry the 1. 1, carry the 1. 1, 1, 1. Base 2. Unless I've made a mistake. Let's see now. How many ones of this is this? One, 2, 3. There's a 1 here. 1 plus 1 plus 1 is 1, carry the 1. So that 1 comes down. Don't you think? So unless I've made a mistake, it ends with 3 zeros and has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 ones. So 3 zeros at the end excludes the last two selections, C and D. As far as B is concerned, there's a 0 between the 1, so that can't be it. So the first one has how many ones? 1, 2, 3, 4, 5, 6, 7, 8, 9. How many ones is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 ones. Let me sort of see what we got here. So this here, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 12 ones, all right. So there's a leading 0, but that shouldn't bother us. So I think A is the correct answer, and oddly enough, I didn't make any mistakes. This is correct, as hard as it may be for you to believe. So there you go. It's a good thing I have the graph paper. That really saved me, actually. Yes, sir. That is correct. D. Well, D is got a rather different look to it, doesn't it? Because look at this. D is got 2 zeros and a 0. Oh, maybe the answers are not lining up. That's possible. So your D might be equal to my A. Okay, sure. Yeah, they're rearranging. It's a blackboard thing. What can I tell you? So the leading zero is the only difference, and if you add a leading zero in here, it doesn't change the value. Does that sort of answer everybody's question about the multiply thing? So the multiplication, I mean, if you think about it, multiplication is really trivial. I mean, you just either copy everything or you zero everything. And then there's this question of how do you do all these additions with all these things coming in. And there's different techniques for building the hardware for that. Some of which can be quite fast and some of which are quite slow, depending on what you're into in terms of building hardware. Let's see, what else do you got here? Any other questions on question 7, homework 7? I don't know, let me see. No, it is not. It is not. We're confronted with a transition phase in the electronic era. We are used to things like transistors and solid-state diodes, and symbolically, they look like this. That's how we draw them, and that's how energy flows in one direction, doesn't flow in the other direction, and these serve as one-way gates of current. And that's a fine thing. But you can implement these in any one of a number of different interesting and wonderful ways. One of which was built on the work of Edison. Edison created a bulb. And here I am trying to draw a light bulb. And in that light bulb, he had a filament. And next to that filament, he had a conductor. And he noticed that he could get energy to pass across this vacuum of space from the filament to this conductor. And he called it the Edison effect. And this is like in the 1800s. He's discovered this. And it's a wonderful thing. He can't think of an application for it. He files it in his notebooks and forgets about it for a while. Along comes a consultant to one of these fellas who came up with this idea of a transatlantic telegraph. So in a place called Sandy Hook, New York, which is a beautiful place in New York Harbor, or off New York Harbor, there's a relatively ancient building where Morse set up a very long antenna. And in that antenna, he tried to transmit across the Atlantic. And you could barely hear what was going on the other side. He wanted a transatlantic telegraph. Sort of real breakthrough stuff over 100 years ago. So he had a consultant whose name is Sir Ambrose Fleming. And Fleming said, let's use the Edison effect and create a detector. And this is the diode. But because he's using a plate, he decides that he's going to have a filament on one side, and if you look at it, it's got a little Edison socket, an A21 Edison socket on it, so it can screw into a lamp, just like a light bulb. And then on the other side, he put in a plate, also with an Edison socket associated with it. Excuse my poor drawing. Here. That's my Edison socket. Lousy as that might be. And the whole thing was incorporated into a glass envelope with all the air pumped out. And he used this as his detector, where energy could only pass in one direction. And in fact, kind of looks a little bit like the schematic. And so now we've got an exquisitely sensitive diode that's able to pick up the telegraphic signals from across the Atlantic Ocean. Now in Britain they called these things valves. In the United States we called them tubes. And so this is called a thermionic valve, or a thermionic tube, or a thermionic diode, or what some people call it, a Fleming valve, or sometimes they even call it, and this is, I rarely hear this term, a canotron. Anything involving electronics usually ends in tron. And so that's a big question, is what should the property be of voltage drop? Now we know from our experience with silicon, we could typically get a 7/10 of a volt drop. But when we're fabricating high sensitivity thermionic diodes, the answer is we have no way to know what the electromagnetic permeability will be for the space in this vacuum. And so the answer is there's no way to know from the given information. It's, there will be a drop. We just don't know what it is. It depends on how it's fabricated, what the distances are, how good the vacuum is, things like that. Whether or not there's a little drop of mercury in there to add some mercury vapor for conductivity. So this... That's not the answer. No, 0.7 VDC, that's for semiconductors, not for thermionic diodes. No. Yeah, so 0.7, that's for, not all diodes are 0.7 either. I mean, you could do a, NRF diode. There are now semiconductor versions which are down to 0.3, but they changed the material properties, and I don't think they're using silicon. So for silicon, you typically expect a 0.7 volt drop. Thermionic diodes not. There's no way to know. Could be much less. I would think it would be much less. I've never actually played with one. Got to get me one of them. So that's the answer to that. What other questions do you have? Thirteen. Multiplication in the computer is done with repeated addition. Well, we've seen how we multiply here. That's very similar to how they do the multiplication in the computer. So the answer to that one is false. Could you do it with repeated addition? Yes, you could. Has it ever been done with repeated division? Yeah, maybe somebody's been doing that. I think one could make a compelling argument that is always going to give you a very slow answer, but it is possible to do it. But that's not normally how it's done. It's time for a new paper. Did somebody say 14 as well? Okie doke. Let's see. The following is a binary multiplier. 2-bit. 2 by 2. So we got 2 bits going. Sure. Oh. Let me just check. Do we do multiplication in the computer with repeated addition? And the answer is not normally, no. we use a structure very similar to this, where we're doing shifting and ANDing with 0 and 1. And so then comes the next question: how do you do a 2-bit multiplication? So I'm just trying to think of the best way to do this. Maybe the way to do it is with a truth table. A1, A0, B1, B0. So what I did was I said that this is the A part, and this is the B part. And what we know is that if we have 0 times 0, the answer is going to be 0. That'll be 0, and that's 0, and that's 0, because 0 times anything is 0. Here we have 1 times 0 is 0. This will be 1, 2, and 3. Here we have 0, 2, 4, 6. Here we have 0, 3, 6, and 9. And that's the 2 by 2 answers. And so what we'd look for in the output, C3, C2, C1, C0 is 0, 0, So that's the binary version of the answer on the left. And so you can see how that works, right? Because 3 times 3 is 3 times 3, which is 9, and here's the binary version of 9. And this is the truth table for the multiplier. Right? And one of the things that you can see, for example, is that C3 is equal to A1, A0, B1, B0. Right? You can just do that by inspection. And in fact, if you think about it, you might be able to do some of the others by inspection, or if you're of a mind, you could number your truth table and do a K-map, which is a perfectly reasonable thing to be doing, I think. But at the end of the day, you're sort of interested in seeing what the canonical sum of products will be, so we can certainly do that, but we'd still want to have the radix equal 10 column numbering, 0, 1, 2, 3, 4, 6, 7, Doesn't look too bad. And now we can say that C2 must be equal to sigma m of, and then you can say it's 10, 11, and 14. And C1 is equal to 6, 7, 9, 11, 13, and 14. And C0 is equal to 5, 7, 13, 15. And so that gives me really the specification for a 2-bit by 2-bit binary multiplier. So now let's take a look and see if we can decode the circuitry that we've got here as it's presented. And so we can say, what I could do, I don't know if I can do that. I was going to say I think it's better if you see the graph paper. So what we'll do is we'll just sort of sketch it out. So it looks like there's 4 AND gates. And this one goes to here and to here. And it looks like A1 goes to here and to here. And B0 goes to here and here. And B1 goes to here and to here. And it's a little bit of a rat's nest. Then it says here this becomes C0. And then there's a C1, C2, and C3. Looks to me like there's an exclusive OR gate going into C2. A AND gate going into C3. Another AND gate feeding that AND gate. And that AND gate takes the output from this AND gate, complicated as it may seem, and then there's another exclusive OR gate. This is fun. Isn't this fun? This is very fun. Another exclusive OR gate that comes in through here. Geez, why don't I just print this out and get the whole thing for you? That might actually make more sense. But in any case, at the end of the day, what you've got, and I've made a mess of it. Sorry about that. I should have done this more neatly. Looks to me like the input over in here is going into an AND gate there. This comes out and goes in there. And it also goes into here. And let's see if there's any more. Yeah, this OR gate goes into the other side of this, and it looks like that goes in down here. I think I've got it. We'll see. I'm going to change pens because this is getting to be a bit of a clogged mess. So then this is going to be A0B1. And this is going to be A1B1. And then over in here, C0 is going to be equal to A0, B0. And C1 is going to be equal to A0, B1, and whatever is coming out of here, which is going to be A1, B0. So that's A1, B0 exclusive ORed with A0, B1. And C2 is going to be equal to, wow, we don't know the output here, right? It's A0, B1 ANDed with A1, B0. Exclusive ORed with, and I guess we got A1, B1. And then comes C3. And now C3 is going to be A0, B1, and so this is A0, B1, and whatever comes in here, which is B0, A1. And then that's going to all be ANDed with whatever this is, which is A1, B1. So A1, A1 is A1. So this is going to be A1, B, well, A1, A0, B1, B0. And that's C3, which matches what we had from over here. So our C3 is correct. You'll want to go through the process of simplifying these expressions in here and making sure that you have correctness. But if this is true when A0 and B0 are both asserted as 1, then here's A0, and here's B0, and they're asserted as 1, and it is true. And here it's true again, and here it's true again, and here it's true again. So that works just by visual verification. And I suppose what you could do in a case like this guy is you could write it out. A1, A0. Well, A exclusive OR B is equal to A, B prime, or A prime B. That's generally true. So if we said let A equal A1, B0, let B equal A0, B1, then you can substitute the A's over in here, and what you get, excuse me, is A1, B0 times A0, B1 prime or A prime, which is A1, B0 prime times B, which is A0, B1. And then you can use De Morgan's theorem in distribution in order to get an answer. Right, so I've applied De Morgan's theorem here, De Morgan's theorem here. Now I can use a distribution theorem. And this is a simplification to 0 because it's A1 prime times A. And so now I have A1 B0 A0 prime, or A1 B0 B1 prime, or B0 B1. And I think you can put that into a canonical form, or you could do a truth table and compare it with this guy. Or what you could do, if you were of a mind, since we're doing C2, which is over in here, is you could see what would make it true. And that's not a bad way to go. So if you have A1 is true here, B0 is true, which is here, and A0 prime is true, which is here, then you would expect to see a 1 for C1, which is true. And you could do that and proceed to examine the truth table. And you can keep going that way, or you can just make your truth table and extract it from here. So there's a couple of ways to do this. Reverse engineering this was not particularly easy. But at the end of the day, your 2 by 2 multiplier is going to give you a correct answer. And so the answer to 14 is true. I don't know if there's an easier way to do that. But you got to reverse engineer essentially what amounts to a complicated looking circuit in my view. And there's no good way to do that except by writing out the intermediate products. And I do that, and then I try to expand it, and then I do the simplification, and then I validate it against my spec, which is over in here. The reason I don't go through and do the canonical sum of products form and get you a minimal sum of products is because my minimal sum of products may not look like this. In fact, it almost certainly won't. And so that forward synthesis doesn't really work. I've got to reverse engineer the circuit to see if it's valid. Any questions about this one? That was a hard one. Wasn't that hard? That was a hard one. Other questions about homework 7? Six and 7. I think we deserve a fresh piece of paper after that little exposition. I deserve a fresh piece of paper. Nobody else does. I deserve it. So, 6. Let's do 6. What is the binary representation of the following negative number in 2's complement? So right away we know this is a negative number. And we want to know what is the binary, the positive version of this negative number. So if you take a negative number and complement and increment it, you should get the positive version of the number. 0, 0, 1, 0 plus 1 is 0, 0, 1, 1. And so this is equal to minus 3, base 10. And that's equal to positive 3. So that's it. For me, it's A, but I don't know what letter it is for you. Blackboard messes these things up. And then, any questions about this? Let's look at question 7. 0 can be represented in all forms except, let's see, is 0, 0, 0, 0, is that equal to 0? The answer is, yeah, that looks all right. What about the 1's complement of 1, 1, 1, 1? Well, 1's complement is going to be the inversion, which will be 0, 0, 0, 0. And so that's okay. That looks all right. Then there's the 2's complement of 0, 0, 0, 0 with a bunch of more zeros. And the 2's complement is going to be 1, 1, 1, 1 plus 1, which will be 0, 0, 0, 0 with a 1 that falls on the floor. And so that's all right. And then the 2's complement of 1, 0, 0, 0. Well, what's the 2's complement of that? And it's going to be 0, 1, 1, 1 plus 1, which is 0 carry the 1, 0 carry the 1, 0 carry the 1, 1, which is what we started with. So this is an interesting point. It's not 0. And so it says 0 can be represented in this form. The answer is no. That's not a 2's complement form. I don't know what form that would be of 0, but that's not a form of 0 I know. Unless you want to call it negative 0 in sign and magnitude. That doesn't work. Negative 0. It's not 0. The 2's complement here is not going to give, this is not sign and magnitude if you're doing the 2's complement. So that does not belong. One of these is not like the other. And so this is not the 2's complement of 0. Any questions about that one? Other questions for me? Sure. Let's see, 18. What do we got here? Write the 2's complement for the following 5-bit binary number. This is question 18. The number base 2 needs a 2's complement, so we're going to complement and increment. The complement will be 1, 0, 1, 0, 0 plus 1. One zero one zero one. Yep, that's a correct answer. Any questions about that? It's just forming a 2's complement. Everyone should know how to do that by now, I think. It's kind of like beating a dead horse. I find that, well, only slightly less cruel than beating a live horse. Why would anybody want to beat a dead horse anyway? It's already dead. And beating a horse doesn't sound like fun either. Why would anyone want to beat a horse? It sounds terrible. And then comes 19. Convert the following decimal number to binary using 6-bit 2's complement representation. What? 2's complement. What? 13 base 10. You want to convert it to binary. Well, 8 plus 4 is 12, plus 1 is 13. So that looks like binary. So that works. That works too. So this is convert the following decimal number using 6-bit. 6-bit. So 1, 2, 3, 4, 5, 6. So there, I added 2 leading zeros to make a 6-bit 2's complement representation of positive 13 base 10. So this is positive 13 base 10, 6-bit, because it's got 2 bits leading. So what this is telling me is that my hardware, my accumulator hardware, is 6-bit hardware. As a result, my quantity 1101 must have leading zeros 00 in order for me to obtain a 6-bit representation of 13 base 10. So that's the upshot of that question. Now, if they had said, find the 2's complement representation of minus 13 in a 6-bit 2's complement number, you would complement and add 1. But he didn't ask for the negative, just asked for the positive 13. How does that grab you? Good, right? Everybody okay with this? Next question, please. Sure. Let's do that. 15. Well, let's see. Time for coffee. All right. What steps do we take in order to form the 2's complement of a negative number? Well, there it is, right? Complement and increment. That's one of the answers. Complement and increment. So that's my way of saying, do you know how to take a 2's complement? And the answer is yes, you do. Complement and increment. And that's what we do. And that's it. Is that everybody okay with that one? So it was 15. That was 15. 16, was that also on the list? Or 17, was it? Because it was 17. Sorry, could you ask the question again? Which ones did you want me to cover? 17, okay. In 2's complement, what do all the positive numbers have in common? Do positive numbers begin with a 1? Would that be a positive number? Well, that'd be a negative number. So positive numbers begin with a 0. So all the positive numbers begin with a 0. What about 0? Doesn't that begin with a 0? And the answer is yes, but it's not a positive number, nor is it a negative number. It's perhaps positive semi-definite. It's kind of positive. I don't know. It's not. We wouldn't call 0 positive, nor would we call it negative. So it's neither. So all the positive numbers, 1 is a positive number, right? 0, I'm not sure. That doesn't seem positive to me. Unless you're an optimist. -1, that's negative. So I would say anything greater than 0, 1 or higher, is a positive number. And they will always have a leading 0 in front of them, showing that they're positive. Does that sort of make sense to people? Okay. Next question, please. No more questions? Are we done? We've exhausted the questions? I think this goes up to like, I don't know, question 30. Oh, sure. 22. You got it. So maybe we get Nice fresh sheet of paper, because it's big science. And let's see now. What is the 8-bit 2's complement, 8-bit 2's complement of the decimal number minus 100? Minus 100. And it's said to be a decimal number, so we know that's not binary. That's decimal. And we want to know how much that is in base 2. Moreover, we also know that this is an 8-bit number. 8-bit. So first thing I want to do is I want to convert 100 into base 2. So I take 100, divide by 2, I get 50 with 0 left over, divide by 2. I get 25 with 0 left over, divide by 2. I get 12 with 1 left over, divide by 2. I get 6 with nothing left over, divide by 2. Get 3 with nothing left over, divide by 2. Get 1 with 1 left over, divide by 2. I get 0 with 1 left over. So 100 is so that's my first step. Then he says something like this, 8 bits. 1, 2, 3, 4, 5, 6, 7. I want a positive 100, so I have to have a leading 0. So all I did was rewrite it with the leading 0, so I got 8 bits. Then he wants 2's complement, because he says, what's the 8-bit 2's complement of the decimal number? So now I got a complement and I got an increment. So now I got 1 plus 1 is 0, carry the 1, 0, carry the 1, 1, 1. And therein lies the answer. Now let's see if this is even remotely close. What is the 8-bit 2's complement of the decimal number 100? Oh, I get it. If you're going to do the 2's complement of minus 100, it's going to be positive 100. So then this would be the answer. Right? The 2's complement of the decimal number minus 100 is basically 100. And so he's asking, this is tricky actually, what is the 2's complement of the decimal number minus 100? So he's saying the negative of negative 100, which equals 100. So that's your answer. Tricky wording. Gotta read the question, I guess. Any questions about that one? That was tricky. So I'm looking at the clock here. It says we have no more time, I think. And so it's a very nice warm day. Enjoy the rest of the day. Bring your questions on Monday about homework 7 so we can wrap this up. Enjoy the weekend. You've got your reading assignment. You're going to be in chapter 5. Let's see how far we can get with this. Yeah, let's stop at the carry look-ahead circuits. You're not going to get too far with that, I think. Carry look-ahead adders is like a deep optimization thing for adding circuits. So we can stop around page 251, but you definitely want to read up to that. The carry look-ahead, I think we can probably avoid that. BCD adders. Yeah, you want to read about the multiplication. So partially, you're going to want to skip to page 266. So omit 251 to 256. $266. So skip that. So we're skipping 251 to 266, reading chapter 5, and that ought to keep you out of the bars at night because you'll have your textbook with you, and you won't want to go into a bar with your textbook because people will look at you funny. Besides, you'll probably end up with COVID or something awful. All right, well, good luck to you and stay safe. Thank you. Thank you. Yes.